Why is it not full screen? Maybe I can go in this way. So hello everyone. I'm Zhe from Princeton University, and I'm happy to introduce to give a presentation about our project Infinigen here. And the title of our paper is Infinite Photorealistic Worlds Using Procedural Generation. It's published at CVPR 2023. I'm one of the three first authors, and these slides are mostly borrowed from another author, Alex. And first, I'm not sure if you have watched the video, but let me try sharing it here.
Can you play the song?
Can you hear it?
No. Oh, yeah, I can hear it.
Is the video clear?
Yeah, perfect.
Nice. Okay, this is a video. Let's start my presentation. Oh, yeah. So to begin with, data is a driving force of progress in computer vision. Data is the signal through which the model can experience and learn to disentangle the complex visual world. Most famously, ImageNet, the hierarchical database, started as a revolution in computer vision. It played a pivotal role in the advancement of deep learning and neural networks, and it is used as a benchmark for the annual ImageNet large-scale visual recognition challenge, which has spurred innovation in image classification and object detection algorithms. And ever since, major advances in computer vision have been precipitated by the availability of large-scale labeled datasets with more complex scenes and richer annotations, like common objects in context, etc. However, collecting dataset in real world and annotating them manually requires a lot of human labor and is prone to errors. Instead, synthetic data is becoming an increasingly promising solution. Synthetic data means rendered images with computer-generated labels. It has many advantages compared with real-world data. First, it has scalability. Generating large amounts of synthetic data is generally easier and faster than collecting equivalent amounts of real data. And it has high-quality labels for many tasks, including depth estimation, object detection, and optical flow, etc. We can also have full control over the characteristics, distribution, and complexity of synthetic data. And we can get rid of privacy concerns by creating data that don't contain sensitive information. For example, this image shows the MPI Scintilla dataset. It is derived from open source 3D animated short films and used for evaluation of optical flow. Synthetic data is useful only if it's close enough to the real world. And we have already seen that the Hollywood CGI is very realistic and has near zero domain gap. Even though these dinosaurs and avatar is not real, but they are realistic and have nearly zero domain gap. Therefore, this progress in the movie industry suggests that we can also make near zero domain gap with synthetic data in various other domains of computer vision as well. Therefore, our work in Infinigen is a generator of unlimited synthetic data. It's not a fixed set of data. In other words, it is a money printer instead of being a fixed amount of money. And notably, it has these key features. It is photorealistic, 100% procedural. It has broad coverage of the natural world. It has high quality labels, and it is free and open source. Here shows a random sample of the generated images from Infinigen. And this presentation will focus on three parts. First, what is Infinigen? I will walk through these key features. And next, how does it work? And Infinigen contains many contributors' works. I will focus on my work on terrain and Alex's work on geometry nodes and creators. Finally, I will talk about how everyone can use it. Let's start with the first part. And to show its photorealism, as we already see in the trailer video. Here I give these screenshots of the clips again. As you can see, they are all very photorealistic. And although the trailer is kind of selected for the video purpose, here we also show a random sample of generated images. They are also have similar quality as the video. Second, Infinigen is completely procedural. This is a procedural clip from that video. As you can see, this flower, everything of this flower is procedural. You can control its center radius, color, and other many parameters using this node graph. And as you can see in this video, we make heavy use of Blender's node graph and also Blender, make heavy use of Blender here. Blender is a powerful and versatile open source 3D software. It's used for a wide range of visual contents, including animated films, visual effects, video games, 3D models, etc. And Blender has comprehensive suite of tools for modeling, texturing, rendering, etc. And it also has it is also open source. and fostered a vibrant community of artists, developers, and enthusiasts who contribute to its ongoing development. With Blender, Infinigen is 100% procedural, generated from scratch. There is no AI, that is, there is no generative models, etc. in Infinigen. Although it is often mistaken to be AI on some social media, but it is no AI, it is graphics only, because we want accurate ground truth, not an imprecise black box. And there is no external assets like ShapeNet. There are no meshes, no image textures that we like borrowed from existing resource. Therefore, we can have infinite variations. And everything has interpretable rules. We have more than 40,000 lines of Python or C++ code you can read and customize. Instead of being a model, we use procedural modeling, that is encoding knowledge and physical rules into randomized programs, which the models can learn from. Next, Infinigen has a broad coverage of the natural world. For example, the left image shows a wide range of leaves, flowers, mushrooms, and pine cones, and the right image shows a lot of sea creatures, including corals, sea shells, sea kelps, sea urchins, etc. And this image shows the diversity of our trees across different seasons, with different sizes, from large trees to small bushes, and with different branching patterns. And this image shows the diversity of different animals, including carnivores like tigers, herbivores like lambs, and birds and beetles and fishes. So you might ask, why do we focus on the natural things instead of buildings, cities, or indoor scenes? First, because natural things are needed for many applications, like agriculture automation, including crop monitoring, robotic farming, etc. Actually, there are also some labs discussing with us for the usage of our data on such applications. Also, they are useful in ecological monitoring, including wildlife pollution, biodiversity, and anomalies. And another important reason is that vision involved entirely in the nature before any human activities. We think nature alone is enough to pre-train visual foundation models because tiny bird brains can already solve many vision problems, including object detection, SLAM, grasping, motion planning, etc. This picture shows all kinds of eyes that evolved in nature. Besides nature scenes, we do have plan to extend Infinigen to indoor scenes or other types of scenes in the future. Besides being realistic and diverse, Infinigen has high-quality labels. High quality means the resolution of the ground truth label is the same as the resolution of the image, which means the size of the faces of the underlying mesh are as small as a pixel. As you can see on the right image, each face is painted with different colors. To emphasize it, they are so tiny that they appear white overall. But if you look carefully, they are each with different colors. Such kind of high quality real mesh is where we put a lot of efforts in this project. And it is important feature that distinguishes us from many typical 3D scenes that are generated in games. Typically in games, they use fake geometry where the leaves are flat, transparent images on square canvas hanging on the tree, and the trunk of the tree is only subdivided for a few times. But it deceives the eyes by altering the direction of surface normals. Surface normals are crucial for determining how light interacts with the surface. And by altering the surface normal, we call this technology fake geometry. It changes the appearance of the surface without changing the actual geometry of the underlying mesh. In contrast, in Infinigen, we use the real geometry, as you can see on the right image. This enables high quality and reliable ground truth labels. Because our assets are procedural, they can be evaluated at any mesh resolution. We make sure that all mesh faces are approximately 1 pixel in size when projected into the camera. As you can see in the figure, as the camera moves further away from the tree and the surrounding rocks, the face size of their mesh increases, which can be seen from a fixed camera on the top row. In implementation, the terrain and other assets handled it differently, as the terrain is a large continuous surface, and the assets have more limited spatial scale. I will talk more about how this is achieved in terrain later. Therefore, with such real geometry, we can extract high-quality labels for any computer vision task. For example, bounding boxes. And bounding boxes can not only be 2D, but also 3D. Also, we can have 3D depths and segmentations. If you remember the segment anything model, we can have a comparison with them. Segment anything is an imperfect model run on many images. It has human notation errors, it lacks fine details, and there's no underlying dataset release. They are only predictions. However, Infinigen is an unlimited generator of datasets. It has pixel perfect detail and is fully accessible. You can see the segmentation labels of Infinigen. It's much detailed than SAM results. And here is a summary of all different kinds of ground truths Infinigen can generate, including mesh, depths, surface normals, occlusions, segmentations, bounding boxes for object detection, and optical flows. Also, we can have the intermediate rendering results because we have the full control of the rendering pipeline, which includes the diffuse light, direct light, or indirect light. Finally, the Infinigen has feature. It's free and open source. It has no paid assets, and the dependencies are open source and free. It has BSD3 license. You can use it for free and do whatever you want with the results. Actually, some part of our code used to be GPL license, but then we moved them away to another separate repository called Infinigen GPL. Therefore, now our main repository is completely BSD license. And we accept open source contributions and feature requests. And more is coming soon. The tutorials and the documentations are actively being updated. Welcome to visit our infinigen.org. And currently it has 4.4 stars and many folks on GitHub. It has a fast growth of star in the beginning and it still keeps going. Next, I will talk about how does Infinigen work. First of all, it can happen because the collaboration of many contributors, many PhDs in our lab working together. And among them, I work on the terrain part, and Alex work on the geometry node and the creators. Geometry node is a tool to make most of the material and the shape in Infinigen. Let me first, it's also important to introduce the scene generation pipeline in order to organize all the different parts of works together. The pipeline is mostly in 3 parts. The first part is scene composition. In this part, we generate a coarse terrain mesh, as you can see, this low poly mesh, and we scatter placeholders of assets like these cubes on the terrain. And we also have the coarse tree structures on the terrain. And the camera trajectory is also determined in this stage. based on some criteria to make the camera views more interesting. And the next is the populating and the meshing stage. We generate detailed assets for each placeholder, and we also give pixel scale details to the tree and the terrain. The materials are assigned to the object either in the first or second stage, depending on the specific type. And finally, we render the images and the ground truth labels in Blender or through other processing code. Let me first introduce the terrain. The terrain is important because it is the underlying ground surface which everything is scattered on. The terrain is composed of a set of terrain elements, each represented by signed distance functions, SDF. For example, we can represent the mountain in the following way. The SDF equals to the coordinate z minus a plane noise as a function of x and y. And we can have more complex terrain elements like Voronoi rocks, as you can see in this image. It can be done in this way, given a 3D point P with coordinate x, y, z. We have a randomized Voronoi 3D graph. We find which cell P is in. Say we found its center of the cell x0, y0, z0. We can have a random hash function based on this center C, and we can sample whether this cell is rock or not according to the hash function on C. If it is a rock, we have SDF equals to a gap size minus the distance to the Voronoi cell boundary as a function of x, y, z, and plus some 3D noise to make the rock more rough. It's very fast to compute and it looks very realistic. And here are also other terrain elements which are represented by SDF, like the wind eroded rocks. I have already talked about the Voronoi rock, and I will talk about these mountains with erosion process later. And we have caves. D shows the interior of the cave, and E is the exterior appearance when a cave is carved out of a mountain. And we also have these imaginary floating islands, which is achieved by putting a mountain on top of an upside down mountain. And the advantage of such SDF representation is that the SDF is written in C or C++ language and can be compiled either in CPU with OpenMP speedup or in CUDA to achieve maximum parallelization. Also, SDF can be evaluated at arbitrary precision and range, producing a mesh with arbitrary details and arbitrary extent. Also, SDF is very flexible for composition. Boolean operations are just the minimum and maximum of SDF, which could be very hard to achieve with raw mesh. And to put a Voronoi rock on top of a mountain, when we find the center of the cell, we query whether this cell is inside the mountain according to the SDF of the mountain. And we only put the rock if the center of the cell is inside the mountain. It's very easy and cheap. And also the noise can be very easily added to SDF function just by direct addition. And the terrain system also includes these land processes on top of the raw terrain generated by noise. We have these two processes, erosion and snowfall. They are from open source code or open source library. And the result, as you can see in these two figures, after this process, the resulted mesh can still be represented by SDF function, although the process runs on a finite resolution grid. It can be represented as an interpolation of a lookup table. For example, after erosion, we have a height map table, and we represent the mountain in this way. The SDF equals to coordinate z minus a 2D linear interpolation of the height map at the coordinate x and y. And to make it more detailed, we just added some noise on top of this SDF function, as I mentioned. And in order to achieve dynamic resolution for the terrain, we proposed some meshing algorithms. The current public code uses such spherical matching cube algorithm. It has several steps. First, in the low resolution step, we divided the visible 3D space within the frustum of the camera and a certain distance range into m by n by r blocks. They are in spherical coordinate and uniform in the angle and logarithmically in r. Then we find all the visible blocks, and then we do high resolution matching cube on this visible block after further subdividing these blocks. Also, we consider the out of view cubes, which has lower resolution than the visible part. In such a way, we can make very efficient use of resources to make the mesh as high resolution as possible. However, for videos, flickering can exist using this algorithm more or less depending on the mesh resolution. This is how the mesh looks like using this algorithm. As you can see, in front of the camera, the mesh has the finest detail, and but the occluded part in front of the camera also has low poly. And to overcome the flickering problem, we have implemented a new algorithm which is based on an octree, and we are going to release it soon. And we also have, before spherical margin cube, we also have some early development which is just based on subdivision. I can show some early results here. As you can see, because it's only based on the subdivision, the mesh looks rounder than current version. And so we can see as the terrain is being improved to be more and more realistic. Except for we use SDF in terrain, all the other parts of the assets make heavy use of such Blender nodes. Let's take a look at this important for Blender nodes. They are promising but limited. They have the benefits that they are easy to generate most assets and interactive editing in GUI. But they have the limitations that the graph structure is fixed and it's hard to integrate with other procedural rules in Python or C++. Therefore, we invented such node transpiler, which can, as name suggests, can convert one language to another. In our case, it can convert the Blender node graph language to Python language. And the Python code is the Blender's API, which in turn can create the Blender node graph we begin with. And the transpiler have many utilities, like adding randomizations to the node graph. In this way, we can make procedural assets more easily. This example shows the node graph you begin with and the resulted code you have with the transpiler. The basic algorithm is recursive tree traversal, and you can have each node corresponding to a line or a block of code in Python. And we use high-level node graph API instead of Blender's original API, because Blender's original API are usually very messy and verbose, and our API supports more functionalities. We insulate, therefore, it insulates project from Blender, because Blender can have API changes and bugs. Also, in the long term, we plan to map it to other inference engines. It also has advanced features, automatic target discovery, various graphics primitives act like Python functions, like node graphs, shaders, and objects. It's similar to the linking stage of a compiler. With the help of transpiler, we made many materials, or more precisely, material generators, as each of them has a lot of randomness in it. Transpiler is important for open source contributions. Artists are usually very talented at critically observing and reproducing the visual world, including 3D artists. They are better than us in creating the 3D contents. However, they may not be good at Python programming languages. Therefore, they can use geometry node. They are intuitive, widely adopted, and growing rapidly more popular. Artists can begin with Blender geometry node, and then with the help of the transpiler, they can convert their geometry node into Python code with just one click and contribute high-quality procedural Python code. And through open source collaboration, here this image shows the cloud, which is made by one artist under a CCCL license. We can just borrow his work using the transpiler. Through open source collaboration, we wish that Infinigen will encompass the entire visual world eventually. Next, we can take a brief look at how creatures are generated. It begins with a tree of body parts with interpretable parameters. The tree, or the so-called creature genomes, reflects the topology of real creature, which don't form closed loop and is modular and compositional. For example, you can create hybrid animals like a tiger with wings or a bear with horns, with the body parts mixed. Creature part generators first generate the individual part. Then the attachment location are determined in this UVR coordinate to combine the pieces together. Then in this way, we can have this variety of creatures. And on top of the round row mesh, we have procedural creature sculpturing, which makes especially the face of the creature more realistic in a procedural way. Because the creature is procedurally generated, we can have automatic rigging. Every creature comes with an animation rig, which is the purple here. And they are with controllable inverse kinematic handles, which is the green box here. Also, we can have cloth simulation for the creature skin, which is not released yet, but we can see a simple demo. Okay, and now we can look back at some of our early attempts in creatures. The left image shows a lot of weird creatures. They are very interesting, but kind of scary. And also on the right is a group of beetles following this monkey Susan. As you can see, the creatures has changed a lot since its early development. And even now, compared with other assets, the photorealism of creatures is still not as good as other parts like the terrain, because the terrain is more easy to make realistic, and the creatures, those things with animations is particularly hard, and there are still a lot of work to do. Now, finally, let's come to our last part. How can everyone use it? First, we provide the user with a hello world example, which is a simple desert scene, which you can run within about 20 minutes on a laptop with 16 GB memory. To make it easy, we use reduced settings for low compute scenarios. which is simple scene, low resolution. And you can see our GitHub for more information. If you run this example successfully, you will see these 4 images, the rendered image and these ground truths, including depth, segmentation, etc. Currently, we mostly support Infinigen on Linux, and we also support other platforms like Mac OS if the version meets some certain requirements. You can also try out different settings based on how much computing resource you have and how long you are happy to wait. We have different settings for them. You can read our GitHub page. And then if you are not satisfied with the Hello World app have more computing resources to generate large-scale datasets, we provide this command. It runs on a computer node or on a Slurm cluster of these nodes. For us, we use many nodes with 8 RTX 3090s with 500 GB RAM each. And most things in the trailer video, introduction trailer video, can be generated using this command. Here are some settings you can see. For example, the high quality terrain specifies the terrain to be high quality. And the molecular video specifies we are going to generate a video with single camera. You can read the documentation on our web page. And here is the approximate computer requirements for single image. They are kind of outdated because they are CVPR version and we have more updates. In these figures, you can see most of the things finish within 10 CPU hour and within like 1.5 GPU hour. These are for single images. And if you want to render videos, the cost can increase a lot because the video contains a lot of frames. We are currently actively doing working on reducing this cost so that datasets can be generated more efficiently. And we welcome the users to train on our Infinigen dataset for different computer vision tasks. Currently, we have some initial results on Middlebury stereo benchmarks. We train rapid stereo on Infinigen datasets without fine-tuning. Although we are not doing well on some of the scenes, therefore not having a good average, but for some scenes like the jade plant and the Adirondack scene, which are mostly natural scenes, we have good results. This is a figure shows qualitative results on plant and Australia Middlebury. Therefore, we can conclude that without fine-tuning, training on Infinigen can generalize well to some natural scenes. But for those artificial scenes, maybe we need to add an extra training set to make it better. And for more information, you can check our roadmap website, which includes a lot of bug fixes. And in this month and next month, we are continuously generating and releasing data. Besides the roadmap, Infinigen welcomes open source contributions for code, procedural generators, and pre-generated data. And the ultimate goal of Infinigen is that it will be an open repository of procedural generators covering the entire visual world. If you have questions for installing and running Infinigen, you can submit issues or email us. And that concludes my presentation. Thanks for your listening.
Yeah, thanks. So Infinigen is definitely a hot project recently. The next is the QA10. Oh, I said Infinigen is definitely a pretty hot project recently. Yeah, so next is the QA10. Anyone, any questions?
So, yeah. Thank you for the very exciting work. And yeah, this is a really breakthrough, and it does provide a roadmap on the future for generating realistic objects and scenes. A very amazing work. And so some questions. You show that it can provide some real geometries. So the essence is to use the SDF, sign distance function. Is that correct?
Sorry, can you repeat the question?
Yes, you show that you generate the real geometry using the sign distance function for the terrain.
Yeah.
And in this case, yep. In this case, yeah, here, just would like to understand if you have some specific like the Voronoi rocks you show here. How can we know